Yeah, so today we're going to cover interpreting the results of complex model predictions. And I'm going to start with a bit of motivation to try and get us kind of on the same page. I think a lot of us are here because we already have motivation. But then I want to go into some math and intuition to kind of describe how we've approached this problem and how others have done it. And then I want to end with just a bunch of examples to just see how this works on real data sets. And hopefully we'll have some time for questions afterwards. Okay, let's start with a basic problem. Imagine you're a data scientist at a bank. You are tasked with building models that are predicting whether people are going to repay their loan. Imagine Susan is a bank customer. She comes in. Her data is going to go through this model, and you're going to spit an output. And if you do a good job, then the bank's going to make more money, right? So you want an accurate model here. And let's just go to Kaggle, right? This is kind of a good reference set for what models typically perform well in these types of problems. In Kaggle, there's often two solutions that really do kind of win competitions. One is tree ensemble methods. This could be random forests or gradient boosting machines. These often do really well when you have some handcrafted features or maybe a lot of different modalities in your inputs. So maybe age and height and weight and stuff like that. Neural networks often perform extremely well for things that have high-dimensional inputs where the variables are correlated, so images, time series models, etc. Okay. All right. Well, in our case, the bank has a bunch of tabular data essentially about their customers or their applicants in this case, and so that means we probably fall into the model with kind of an ensemble tree-based method would perform best here. Okay. So if we do that, we'll use XGBoost, one of the more popular versions of this, and we can apply that to our entire customer data set and learn a model. Okay, pretty straightforward setup here. And when we do that, in this case, let's say we end up with a chance that this person, Susan, is going to repay their loan at 31%. Great. All right, data science job done, sort of. But no loan for Susan, unfortunately, for this person. First question, obviously, is why? Why did Susan's loan get denied? Susan wants to know, typically. Your boss might want to know. If you're a good data scientist, maybe you want to know. And often the law wants to know. There's lots of reasons you need to understand why. But this puts us in a situation where, I don't know, a lot of us find this trade-off. Okay, there's a trade-off between interpretability and accuracy. And that's because explaining complex models is often hard. And XGBoost is a complex model. And these complex models are often very accurate because we have very large data sets, and so their flexibility allows them to capture a lot of nuances. But interpreting why they made individual predictions can be challenging, and you're often not quite sure. Now, an alternative, of course, if you want to be able to explain these things, is just to use a simple model. But that has the unfortunate trade-off that it isn't flexible enough to capture the intricacies of your data, and so we're left with less accuracy. Okay? So we can be interpretable, or we can be accurate, and we're stuck with this. We can only choose one. That's pretty unfortunate for the bank, because accuracy is directly tied to money, and interpretability is directly tied to happiness and legality. I won't ask which one they pick. But let's imagine we're still in this data science shoe, and we're trying to solve this. Well, maybe the first thing we're going to do, we picked XGBoost, right? Let's imagine we're in Python. We can just call getScore, right? This is going to tell us the important features. And if we do that, just by default, it's going to spit back the number of splits that it did on all the features. Okay, so XGBoost is a way of training thousands of trees of, let's say they're depth 4 or 10 or 100 or whatever you picked. In those trees, we've greedily chosen splits on the features, and this just counts the number of splits. Presumably, if we split on a feature a lot, it's because it was important. So it looks like age seems to be particularly important here, maybe how much they've worked per week or years in school. Okay. But we want to be careful, so we try out the different options that come with getScore, like maybe cover. Cover turns out to multiply the split by the number of people who went down the split in the training set, right? Like if a split is followed by lots of people, that might make it more important. Unfortunately for us, our supposition that age was the most important totally reversed when we did this, and now occupation seems to be the dominant feature. So we're not quite sure what to tell Susan or our boss. There's a third option here called gain. If you guys are familiar with XGBoost, you'd be familiar with these. Gain is essentially saying when we split on this feature, how much did the loss go down, right? So whenever you're splitting, you're trying to get a better training loss, trying to make better accuracy. This is essentially saying, at each split, how much did we make progress toward that in the training set? When we do that, we again switch which feature is most important, and we get marital status. Okay, so I would argue this isn't quite interpretable yet, not the least of which is because I would consider gain probably the most justifiable choice among these three, even though it's not the default in Python. But it's clearly what choice you make really matters. Okay, so one issue here, because we've got two problems here. One is we're trying to explain the whole model, right? And an entire model is by definition complex. Like the entire thing has a lot of features in it. And if you try and explain how that behavior happens everywhere, you're going to run into trouble. And if, however, you just focus on a single prediction, which is really what we care about Susan right now, then we have a better hope of being able to approximate what's going on here, right? Because it only involves a small piece of the complexity. We're not touching all of the model when we're explaining one instance. Okay, so that's one point here. And so if we follow that, just going to try and be real practical here. Let's go back to XGBoost and see what it has, right? So this year they added a new feature from something out of MSR suggested. It essentially tries to explain a single prediction, just what we want. Great. All right. So it measures the impact of a feature as the change in the expected model output when splitting on that feature. What does that mean? Okay, let's take a quick example. Imagine we have a really simple tree. We're just a function here is just married and you're older than 20. Okay, so that's our function. If you're married and older than 20, we output 100. Otherwise, 0. Now, if we were to write that down as a tree, we could split on married and your age. And if both of those are true, we're 100. Otherwise, we're 0. Okay, so it's just a very basic example of how this is going to work. Now, we'll assume that in the training set, we fall equally into all the leaves. And so the expected value here, if you just take the expectation of your whole training set, what's the expected output of my model? You don't tell me anything about the people. It's 25. Then, if I condition on the fact that I know you're married, what is your new expectation? Well, now it's 50, because it's just 100 and 0. And if I condition on everything, I just get the output. Okay? So I can walk down the tree and kind of check the differences. Well, what was the difference when I conditioned on married? It was 25. What was the difference when I conditioned on older than 20? Well, it was 50. Great. Marriage must be worth 25 of the output, and age must be worth 50 of the output. Okay? That's how this method works. Now, you might have noticed a problem here, though, and that is it's an AND function, and it's a bit odd that one of them is twice as important as the other. And we can make that even more poignant by simply increasing the importance of age. Now, naturally, we're going to split on age first now because it's most important, and our expected value is 30. We condition on age now. We get 60, go down to 110. We do the same method, and we flipped. We've totally flipped. Now, marriage is more important than age, which is totally untrue because what we did is actually made age more important. Okay, so what we have here is an inconsistency. We have where we've made our model clearly depend more on this feature, and yet our explanation totally flipped. Now it's going the other direction. Okay. So if you're like me, I'm not quite ready to go to my boss or to Susan and tell them what was going on because I'm a little uncomfortable with kind of the state of things. Okay. All right. So nothing seems to do exactly what we want, but that kind of begs the question, what do we want? And now I want to take a step back and be a bit more, hopefully not vague, but at least general, and try and discuss these methods at a higher level. What we really want, I would claim, is model-agnostic interpretability. Right? We would like to be able to interpret just viewing our model as a black box. So we don't have to worry about how complex it was or how simple it was. We just want to be able to understand with a good explanation, regardless of the complexity. This could be a tall order, but if we were able to do it, then we could still explain predictions, and we would no longer be stuck in this trade-off. We would no longer have a trade-off between accuracy and interpretability. So, of course, we'd all love this magic blue box, but what is that? In the bank, it'd be particularly nice because then money would no longer be separated from legality and happiness. It could choose both of them. All right, let's try and be more specific here, though. These are all just words, so let me change them into some notation. We'll do a little bit of math here. So let's call our data very creatively X, our model F. You can probably guess what our prediction will be. And then we're going to name our explanation G. Okay, but you guys probably have a pretty good intuitive feel for what X is and what F is, because you use those all the time, and what f of X is. But what is G? Right, that's kind of a question. What is an explanation? Anyway, can I ask you guys, just think about that. If you were to try and come up with what is the mathematical entity that an explanation is? Like, what kind of type of thing is that? It's something that answers why. And I would like to say here that it's an interpretable function that approximates the behavior of f. In other words, G is a model. Okay? And one kind of result of this is that if you have a simple model, it can be its own explanation, right? So if f is just a linear model, and you're really good at understanding linear models, then G can just be f, right? But when f is more complex, then G needs to be simpler, because G is a model that, as humans, we can understand. And if you're a data scientist, maybe G can be more complex. If you're someone who's less familiar with data, maybe Susan, it might need to be much simpler. Okay? But in general, we're going to say that an explanation is a model, because it needs to represent how f changes. So we'll give it a name, call it the explanation model. And that's distinct from your original model f. So this magic box here is supposed to spit out explanation models that we can understand and that are good approximations of f in the regions we care about. So this is really an explanation method, right? Now, one thing I want to stop and point out here is that this means, under this definition, that every explanation method has some explanation model, right? And that means when whatever method you're using, it's worth thinking about what is the model it's spitting out. What does its explanation actually mean? Okay. It also has another thing that we're going to use here, another implication, and that is that we can group explanation methods into different classes based on the types of explanation models that they produce. So if there's a whole range of different methods that produce an explanation models that are all in the same mathematical structure, then we can compare them and make some progress in organizing this field. Does that make sense? Okay, a couple details before we jump in here. One is that an explanation model doesn't need to take the original inputs. It can often take some sort of simplified input space. If you guys are familiar with Lime, they try and do local explanation models, and they use interpretable inputs. But what we'll find is that a lot of methods implicitly do this. Okay, your explanation model will take in some input in a simplified space, so that simplified space might be just a binary vector, and it might represent your feature being present or absent. Okay, and then we'll have some mapping, which is specific to the current thing we're trying to explain, which could then take that back to a full thing we could run through our model. So if you give me a binary vector that says missing or absent for a set of words, then I can map that to their word vectors, either as 0 or the actual vector, depending on whether the word is missing or not. That's what h of x does. And then finally, inspired by how Lime does this, it's often important, like we described earlier, to only explain f around the prediction we care about. Right? We don't need to explain this for Bob and Jill and Fred. We just need to explain this for Susan. And then we can repeat this process again when we're explaining it for someone else. So the explanation model can be specific for a particular prediction. It doesn't need to explain all of f. Now, if f itself is interpretable, of course, it could explain all of f. But we have a better shot if we just try and explain f for this x. Okay? So what this means is that we want our explanation model G, with its interpretable input, to be very similar to the output of our real model when we run the same interpretable input through it, whenever that interpretable input is close to our current input. Okay. All right, so given that notation, what we can do is define a class of methods that have a specific form for G, and that G is a linear model where the interpretable inputs are binary. It's pretty straightforward. You can kind of think of it as a feature attribution method, really. It divides up among your features. It attributes your output, kind of cuts it into pieces and divides it up among your features. That's really what this does. Because you essentially turn your features on and off, and then the fees here are going to be weights that will be the importance of each of those features. It could be negative or positive, depending on whether they cause the output to go up or down. Okay. So I guess what I've done is I've backed up a little bit. I've made a lot of high-level, perhaps hand-wavy statements about how we can group these into classes and how we can view these things as explanation models. But why does this actually matter? And that's what I want to go into next. And to do that, I want to first note that this isn't just a vague class, but it's a class that includes a lot of current models. Okay? You may be familiar with some of these methods. Some of them are model agnostic. Some of them target neural networks specifically. Some of them target tree ensemble methods specifically. Some of them are even targeted at linear models when you have lots of collinearity present in your data. Okay? LIME is a model agnostic method I talked about earlier. Shapley value sampling and quantitative input influence are methods that are based off of Shapley values from game theory. We'll talk more about them later. Layer-wise relevance propagation and deep lift are both things that essentially run a forward pass through any deep learning model you might have, and then backprop through the network differences from some reference value, and end up at your inputs with some kind of importance for every input when it changes from a reference value to the current input value. Okay? And then Shapley regression values are related to, again, the Shapley values from game theory. And the path expectations are the ones that are currently implemented in XGBoost that I just talked about. Okay? All right, so that's the first thing. This class, I would say, is interesting because it's large. It includes a lot of current methods that many of you may be using. It's also interesting for another reason, which is perhaps surprising. And that is that there's only one solution, only one method in this class that follows several desirable properties. The first desirable property is local accuracy. It's kind of a feature attribution method I described, right? It divides up the importance of your features. So it's only natural that it would divide up the output of the model for your current x, such that your features sum to equal that x. In other words, the explanation should match the original model for your current input. So if I want to be accurate near my current input, I should at least be right for my current input. I may become less accurate as I move away from it, but I should at least equal it at that point. Okay? That's local accuracy. The second one is missingness, which may sound complicated, but it's actually followed by all of these methods already. And it simply means that 0 means your feature isn't important. Okay? So simplified inputs such that they're already 0 should be attributed no value. That often means if you have missing data or you have a reference value of 0 and it comes in as 0, then all of those should be attributed no importance. Okay? So it essentially means that 0 connotates some type of missingness. So features that are unobserved should not impact your output. And then the final one is consistency. And consistency is essentially if you change your model to vary more when one of these interpretable inputs turns on, then your attribution certainly should not go down. And that's exactly the problem that we observed when we were looking at the trees. Right? We saw the tree, we added more importance to age, and then suddenly it flipped. And it went the opposite direction of what it should have gone. And consistency says we're guaranteed never to do that. So under these three, I would hope, fairly natural criteria, it turns out that there's only one set of solutions, and they come from these Shapley values in game theory. Okay? So these methods that were leveraging these Shapley values are consistent with these. The ones that are not do not actually follow these properties. So you can say, well, there are 7 different methods there. I'm not going to go into all 7 different methods. We have a paper on this if you want to look at the connections with all of them. But we do propose what we call Shap values, which are essentially a unification of these methods that correspond to these values. And how they work is essentially that their impact is measured as we change the expectations, very similar to how we did with the trees. So imagine that you start at 0, and you just want the expectation of your model. That's E of fx. So this is, I don't know anything about you. What would I predict as a model? I see nothing. And then you pass one feature to the model, and you say, how does your expectation change if I just tell you this one feature? Okay, well, the change when I gave you that one feature is now phi1. Right? Just like when we were going down the tree. When I gave you features, I attributed the difference. We can continue to do that all the way until we get to the current prediction f of x. And we've essentially divvied up among all the features the credit for getting from our expected value to our current prediction. Right? That's my base value, my mean prediction, to my current prediction. I've explained how I got there. And of course, we saw that that didn't work when we did it with trees. So it turns out that order matters. How you add these, what order you do it in, changes the output you get. And so Shap values average over all n factorial possible orderings, which, as you can imagine, is slow. But I think is a very simple way of defining it. Yeah? Yeah, you can go ahead.
How do you choose which one is X1 My first question is, how you choose which feature is X1 and then X2, X3? How would you like rank
Yeah,
them?
how'd you pick the order? Yeah, well, so X1, X3 simply represent all the inputs of your model.
Is there a certain way where you pick which one comes first, or?
Yeah, exactly. So there is, and it's try all of them and then average. So you do all n factorial possible orderings,
Okay.
and you compute fees for all of those orderings, and then you average them. I'm not going to say you actually do this in practice. I'm just defining what the features actually mean. So if you were to compute these from like first principles, open up a game theory book, this is how they say you would do it. You go through and you would do it for every possible ordering. You would get these values, and I would get n factorial possible phi 1s. And I would take the average of those.
Okay. Actually, that was kind of my second question regarding like, if I want to put this technique in my production, like how much time is it going to take to explain my prediction?
Exactly. Good question, and we're going to get there.
Okay, thanks.
Yeah. So to start answering that question, let's draw some connections to some of these other methods. Okay, because I mentioned they were all in the same class, and Lime is a pretty popular one, and so let's connect it to that. So if you've used Lime at all, you know that it twiddles the inputs and fits a linear model to that, and that's the complexity. So essentially, how many samples do you draw is sort of how complex it's going to be. And so this is the equation that is in the Lime paper. I'll kind of highlight what it means. So essentially, you're taking the minimum over some g. This is a class of interpretable models. They have a loss function that forces your g to well approximate f locally. And what does local mean? Well, it means that there's some kernel, pi x, that specifies locality. It's usually like some exponential kernel in your space. And then they optionally have some regularization parameters. So, okay, so this is Lime. But this kind of begs the question in this setup, how on earth do you pick your class of interpretable models, your loss function, your regularization, and your kernel function? Right? These are all things that need to be chosen in this framework. How are we going to do that? Now, Marco and Carlos made very good choices, I think, but they were heuristic choices. But since we now know that they're in the class of additive feature attributions, and we know there's only one right answer, that kind of begs the question, if G is the linear models, we know it's in this class. Okay, so if they choose G to be linear models, which they do in the paper, and X prime is binary, which they do in the paper, though you could generalize it to other things, then it's in the SHAP class. So if you're using Lime with any of the examples on images where you're toggling superpixels on or off, or you're using text and you're toggling words on and off, or you're using tabular data and you're taking it missing or not, all of these are in the additive feature attribution class. That means that the Shapley values are the only things that satisfy these axioms. That's great, but what about these parameters? And sorry, efficiency and monotonicity are just different names for the axioms. Well, it turns out that we found the parameters that convert Lime to produce these answers. And this is a much more efficient way of computing these values than all n factorial permutations. So if you want a model-agnostic way of estimating these SHAP values, you can simply swap out the kernel in Lime with that kernel right there. And if you do that, you'll end up with a local approximation that coincides exactly with these values from game theory and hence satisfies consistency. Now, that's not a total definition of the runtime accuracy, but that is probably the fastest way to compute these values that we know of. The other methods before just used random sampling of the permutations. They would just draw a random set of permutations and take an average, and you're going to get an estimate. But here you can use regularization and other things to get better sample performance. So does this help? It turns out it does in many situations. So if you come up with functions that are perhaps unintuitive, but not that unintuitive, let's imagine you have a simple function. If you have fever and cough together, it outputs 2. If you have just one but not the other, it outputs 5. Otherwise, it outputs 0, and we'll assume most people aren't sick. If we do that and attribute the values, Lime has this local model where it sees the difference between 2 and 5 being very negative, and so it tends to say that fever and cough are both actually protective. But that's not true in this case, and we tested this against a bunch of people on Mechanical Turk and asked them, how do you think you would like to allocate this? and found better agreement with human intuition. We also replicated a test from DeepLift, which was the neural network model. DeepLift has actually updated their code to to better approximate these Shapley values after our work here. And so that's the new DeepLift. Their original DeepLift is improved by that, you can see. And what they're doing here is essentially explaining a convolutional neural network on MNIST, and they're trying to highlight which pixels explain that it's an 8 and which pixels explain that it's a 3. And then in order to test how well they've done that explanation, they erase the pixels that are most like an 8 and least like a 3, and then see how much that changes the log odds to make it look like a 3. Okay? So essentially, if I've done a good job explaining what's 8 and what's 3, I should be able to erase this thing and make it into a 3. And if you replicate that over lots of runs, you can see that better approximations of SAP values tend to perform better in this task. Okay, so we have both theoretical motivation, but we also have some practical motivation. Okay, let's get back to our example. How do SAP values actually work for Susan's loan application? We had a bunch of inputs here, which are fairly tabular. And if we think about this, what's the base rate of our prediction? It's 26%. This is the expectation of our model output on our training data set. Okay? So this is expectation of f of x. This is the prediction for Susan, 31%. And we're really trying to explain how we got from base rate, we knew nothing about we didn't know anything about Susan, to after we observed all the attributes of Susan, we got to 31%. Okay, so no attributes, we get 26%. Let's just try turning these things on like we discussed earlier. If we put capital losses in, we get 25%. What does that mean? Well, if we draw it as an arrow, when we observe capital loss, the chance of her repaying the loan actually drops a bit. You have to have money to lose money, I think. That's probably the intuition here. So now if we only know that we have capital losses, the prediction changes to 25%. Let's learn more and more about Susan now that she is in police and fire. Again, we're just picking an arbitrary ordering here. We now see that this drops to 24%. Apparently that's not the highest paying profession. She works 40 hours a week. She has no capital gains. Her age doesn't matter, turns out, even though we thought it was at the first thing. And then the fact that she's married, that drives a huge prediction on this. The reason is this is actually from the standard UCI census data set, and it's reported from tax returns and trying to predict people's income. And of course, if you're married, you make twice as much because you're reported jointly. Okay, so this is how she got to 31%. And I think this is what we can consider a fair explanation of why Susan's loan got denied. Essentially, she was really helped out by the fact that she was married, but everything else about her pushed it even lower. And by default, we reject most people because their base rate's 26%. Okay, this is SHAP values. And remember, what we really did in order to compute these was averaged over all permutations in some computationally efficient way. Once we do this, we've written up a kind of a Jupyter Notebook visualization that you can use, and it looks like this. Kind of shows some features pushing the risk higher and some features pushing the risk lower. They sum together to be the output. And once you have explanations like this, often you want to explain more than just a single person. You want to get an intuition on the entire data set. And if you do that, you can spin this thing sideways and just sort of stack them for lots of people and just see what we see. And if we stack them in an ordering, imagine there's a hierarchical clustering, like a dendrogram, sitting on top of this. Okay? So similar people are grouped together. And by similar, I mean similar in their explanations. And so we'll call this supervised clustering, where essentially instead of clustering by the original input features, which could bring up any kind of clusters, we will instead cluster by our explanations. And that will cluster people who are similar for the reasons we care about. Right? Because I could cluster you by whether you're good at tennis, I could cluster you by whether you like sushi, but if I'm trying to cluster you by whether you're going to repay my loan, none of those clusters really matter. What matters is features as they relate to this model's output. Okay? So if we do that, we find really interesting clusters in this data set. We find a whole group of people who have large capital gains and large capital losses. And it turns out that if you have lost a lot of money off of investments or gained a lot of money off of investments, you are very likely rich. No surprise there. But this is an insight into a data set that we just pulled out by explaining lots of people, sorting them by their explanations, and then just looking at it. And if we do that through all sorts of different subgroups in here, we find people who are young and single getting put together. We find people who are highly educated and married being put together. There are all sorts of subcategories of people that makes sense with respect to an output. That's why I call it supervised clustering. It's a clustering that is meant to respect the structure of your data set with respect to a certain prediction. And it's built from your model. OK. So that was a simple example. In a little bit of time left, I thought, let's just download a large data set, run an XGBoost algorithm on it, and explain lots of stuff. And what I chose was League of Legends ranked matches. I don't know if you guys know about League of Legends. I'm not a player, but it's got a lot of very interpretable inputs that none of us need background to understand. I think we can understand that if you die, it's bad, and so on. And also, I haven't mentioned this, but we recently released an analytics solution to this for ensemble tree methods. Okay, so rather than having to do a sampling approach like we did for the line kernel, we can actually just solve it directly for methods such as XGBoost and LightGBM. Okay, these are both now merged into both those software packages. So if you have the master version, like more recently than a week or two, maybe 2 weeks for XGBoost and a month for LightGBM, then you can just call pred contribs as one of the options in Python, R, and maybe Julia. Okay. All right, so to get this started, what we're going to do is explain the log odds. So we're going to explain the margin coming out of the tree. And I just want to give us all a quick intuition of that. Since we're going to be looking at a lot of log odds, this is a logistic function. So just remember, when your log odds change by 3, you change your log odds by an order of magnitude, your odds ratio by 3 orders of magnitude, and that can kind of change you from like 50% to, I want to say like 5% outcome. Okay? So these are large changes in probability. So we can start by just explaining the prediction of a single player. What we do is we take all the stats for that player during the game. This is a team-based game where there are 2 teams, and the whole team either wins or loses. But we're trying to predict just based on a single player's stats. We don't know anything about the rest of the team or the other team. And this is just an example of what it looks like to do this in XGBoost. I've got some Python code up on top. You say pred contribs equals true, and I get an entire matrix for whatever data set I passed in. Okay, so this is going to be a matrix where the number of rows is going to be the number of samples in that data set, and the number of columns is going to be the number of features in that data set plus 1, where the last column is going to be the expected value of your function. So it's kind of like that phi 0 in our slides. So then we can do the same prediction that we did for the census data set, except now we have lots more features. And we can see that this person is very likely to win the game because they didn't die very often. Their death per minute is fairly low. They spent a lot of gold per minute, and their longest time spent living helped them. The biggest thing against them apparently was that they, how many minions they killed and how much gold they earned. Okay, so you can kind of see a breakdown of exactly why this player was strong or weak as far as the model is concerned. Okay? Now this is not a causal model, important to remember, but it is exactly why the model thinks this person is likely to win the game. And this model is a fairly complex model trained from 180,000 games, so there's a lot of complexity in here. So one thing we can do, though, with these features is to say, well, let's not just look at a single person again, but let's take all of the people and plot the importance of gold for them. And then, so on the y-axis, we have the SHAP value for gold earned per minute. Now, in this game, which my understanding is that the more you damage stuff, the more things you hurt, the more things you heal, the more gold you earned. So just doing good stuff earns you gold. So it's good to earn more gold. But how much it matters has been quantified here in the model. And so you can see that the gold earned per minute, as that goes up, you see a strong upward trend. And if you're familiar with a partial dependence plot, this is kind of similar to that, right? If I just take one feature and vary it back and forth, a partial dependence plot will give me an idea of how the output is going to change my model. But what this gives me beyond what a partial dependence plot gives me, let me see if I have a cursor here, is you can see a vertical spread. And what is that? Well, apparently, even though my gold, I know how much gold you earned, right? Let's say you all earned 250 gold per minute. That doesn't necessarily mean that it matters the same for every person, because this is not a linear model, right? There are interaction terms. Like, this person's may be a specific champion, and so it matters more to earn more gold. Or this person may have died fewer times. And so all the interaction terms change how much it matters for that person. And so vertical spread tells you the interaction effects and how much they change the importance of this feature. Okay? If there was no interaction terms, there would be no vertical spread. You would just see a line. Okay? We can do the same thing for other things like impact the depth of all predictions. And again, you get to see an understanding of the interaction effects and the change over, I think this is like 60,000 players. Here we can see things like assists per minute. This is how many times you assisted killing someone. And again, we can see that the spread actually matters more as the assists get higher. This kind of begs the question, what's driving that vertical spread? What are those interactions among these features that are driving these explanations? But before we get there, imagine taking this plot and just projecting it onto the y-axis. If I do that, I can then plot lots of these. I can plot the gold, the deaths, the assists, and a whole bunch of other things, and I can sort them by the absolute magnitude of their importances. And so this is kind of a replacement for those bar plots I was showing you earlier, where now we've got some theoretical guarantees that we're not going to have any of those consistency problems. And also we get to see a spread. These are just a dot plot of all the different individuals in our data set and how much that feature mattered for that individual. Okay? And so what we see is that gold earned can matter anywhere from +6 to -6, whereas something like how many times you killed an enemy in the jungle is always less than 2. And you can see some of these are not balanced, right? Like number of turret kills can really help you, but it doesn't hurt you too bad, et cetera. So I think this gives you a more in-depth insight than simply a bar. And I think it comes with some nice theoretical guarantees. Finally, you can look into why exactly these things are having interaction effects by coloring them. So what we do here is we simply search for the other feature that has the most interaction with this feature, and we plot it color-wise. So here we can see that the change in how much your gold matters, like why there's a vertical spread, is driven primarily by how much damage you've been taken. I don't know why. But you can see this for many of these features. Okay, so this is how many assists you had. So if you had a lot of assists, dying so much doesn't matter as much. But if you haven't had very many assists and you died a lot, it's even worse. And then here we go and we look at the assists and we can see that really the spread was driven by 2 groups of people, one who made a lot of gold and one who made little gold. Okay. You can imagine these same kind of plots on your data set, hopefully. And understand, like, when I'm using these complex models, what's driving them, and how can I understand what's going on in them. Okay, we've got lots of examples of these things. Some of them are kind of interesting. Like, here's a reversal of champion level is like how experienced these players are, and you can see that people who die a lot, who are low-level champions, it's worse for them. But actually, if you die a lot and you're a high-level champion, then your champion matters more. It's kind of these weird interaction effects that are important to tease out of your data, and you would not get these with something like a partial dependence plot. Okay. And these are enabled by the fast tree method, so it only took like, I don't know, less than 30 seconds to explain like 10,000 of these things. So what's a practical summary here? When you explain something, I would argue you should ask what explanation model you're using. I think that's a healthy question to ask because it forces you to be concrete about what your explanation means and how you should interpret it, and maybe even more importantly, how you should not interpret it. I think it's easy to misinterpret what these things mean. SHAP values represent a theoretically grounded additive feature attribution solution. So if you're looking for explanations that follow that class, then you should consider that, or consider methods such as Lime or DeepLift that have ways to adapt them to match it. And always ask why. I think it's important to ask that in all these things. Okay, if you want to do this yourself, we have some Python code online. You're welcome to try. If you're doing model agnostic estimation, usually you need hundreds or thousands of model evaluations in order to sample it well enough to get a good approximation. Okay, and TreeShap and XGBoost and GBM is exact and very fast, so I don't see any reason not to use it for those methods.